Hey guys, here we will be talking about the Jacobian Matrix. Before you watch this video, make sure that you've gone over over coordinate systems. You can watch my last video to go over that. So here I've drawn the Jacobian Matrix, and here I've drawn a little expression or a little equation. You might not know what any of that means. In this video, you're gonna understand what that actually means. So, what is the Jacobian matrix? Well, in my last video, I talked about how you can have one coordinate system, like the Cartesian system, and actually compress this system. And you can compress this system and making it become the AB system. And then we can stretch this system as well. Make it become the, say, new system. You can do so many things to the coordinate system to actually change it. But we talk about what happens to the actual x and y axes. What happens to the actual basis vectors? Well, to find that, we have to use the good old multivariable chain rule. So, let's say I have the XY system and the AB system that I've used previously. The XY system has the respective basis vectors, the X basis vector and the Y basis vector. Similar thing with A and B. Now, let's say we have A equals 2x and then B equals 2y, meaning that x is 1/2 A, B is 1/2 y. So, if A is 2x and B is 2y, then how does the basis vector change from x to y? How does it happen? To understand what I mean, let's just draw the whole thing again. I have x and y, and then we have, actually let's draw a much bigger one. Here I have the x basis vector, and here I have the y basis vector. This is the XY system. In the AB system, this system will compress by a factor of 2. And here we have the AB system. If the system compresses by 2, but what factor is the AB system multiplied by from the XY system? What factor is that? You probably already know what it is, but let's actually do that mathematically. So A equals 2x, B equals 2y. How do we transform from the x basis vectors from the x and y? How do we transform from the Cartesian vectors to the AB vectors? Well, we use the multivariable chain rule. Partial A vector equals dx over dA, x vector plus dy over dA. So we are just writing the A vector as a linear combination of the Cartesian vectors. That's all we are doing. Next over. Sorry, this should actually be a partial derivative. Since we're dealing with vectors, these should be partial derivatives. This is just the multivariable chain rule, by the way. Okay. So we have our two equations to solve. So let's solve them. Let's solve this one first. Get this one out of the way. What is partial x over partial a equal to? Well, let's just plug in x. X equals 1/2 a and y equals 1/2 b. So partial derivative of 1/2 a with respect to a. Well, that's just going to give us 1/2. You can do the same thing for y. So we can do the same thing for partial y over partial a. Taking the y value, that's 1/2 b. There's no a term in here, so that just equals 0. So you've already simplified this down to 1/2 and 0. Let's do the same thing for this factor over here. Partial x over partial b, we find that's partial x over partial b will actually give us 0. Because there's no b term over here. And then partial y over partial b will give us 1/2. So we get 0 and 1/2. Right, now, do we have to solve for these as well? No, we don't solve for them. These are the vectors themselves. Those are the actual vectors. So, we've gotten the transformation rule for these two. Let's erase this mumbo jumbo over here. Erase this. And just like that, it's pretty easy. It looks hard, but it's really easy. You could probably do this in your head. So, let's actually simplify this from there. This whole thing goes to 0. We can just ignore that. This whole thing goes to 0, so we can just ignore that. So, that means partial r over, so the a vector equals 1/2. It's half of the x vector. The b vector is 1/2 of the y vector. And that's from the system xy to a b, where a equals 1/2 x. When a equals 1/2 x, and b equals 1/2. When a equals 2x, and b equals 2y. So let's actually draw these vectors out. This is the x vector, and this is the y vector. They're both unit vectors, by the way. Then our a vector would look like this. It's going to be 1/2, that size. And the b vector would look like, would be 1/2 of y. It's pretty simple, guys. Pretty simple. You can rewrite this as ex. You can rewrite this as ey, just convention. You can rewrite this as ea, And we can rewrite this as AB. So we can already see that EX equals 1/2. EA equals 1/2 EX. And EB equals 1/2 EY. Great. So you can probably see what, well, if EA equals 1/2 EX, then EX has to be twice EA. It's intuitive. So yeah, and I'm not gonna go through the math for writing the x vectors as a linear combination of the a and b vectors, and the y vector as a linear combination of the a and b vectors. You can do that yourself. You'll get that the ex vectors are twice the size of the ea vectors, which we can just prove intuitively by multiplying both sides by 2 for each of these. So let's actually do we can actually do something a little bit fancy right here. Let's actually put back those zeros that we had. Let's put back those zeros. 0. So let's actually just erase this. We can see from here that these constants over here, they kind of look like a matrix, sort of. What if we just stored these numbers? What if we just kept them at the same position and then just put some brackets on the left and right side? We have a matrix, and that matrix is called the Jacobian matrix. That's what it is. It's really easy. That's just what the Jacobian matrix is. We just store these numbers in the matrix with the corresponding side. And this Jacobian is it takes us from the old basis to the new basis, with xy being our old basis to AB being our new basis, since we multiplied by our old basis to get our new basis. So that's the Jacobian, or the forward transform, as you can call it. It's a forward transformation for your basis vectors. Well, if we actually calculated what if we calculated the matrix from going from our a vectors to from our a b vectors to our xy vectors? Well, we would get a matrix that looks like, what would that look like? Well, it would have zeros over here, and these would be 2s, I believe. 2s, right? Yeah, they would be 2s. And we wouldn't call this J. We would call this the inverse Jacobian, actually, because we're calling the Jacobian the transformation from our xy system to our AB system. That's the forward transformation. To get from the AB system to the xy system, we use the forward transformation, the Jacobian, and to go back from the xy, we use the inverse Jacobian. The Jacobian we use is called the inverse Jacobian. If we define the Jacobian if we define xy as the old basis, if we define AB as the old basis and xy as the new basis, then this would be the Jacobian, and this would be the inverse Jacobian. But we are just going to define xy as our original system. That's what we are going to do. So these are just pretty much forward and backward transformations, and we can actually store. We could store the x and y vectors, we can store them as a column vector. And we can multiply these by the Jacobian matrix, which would be 1/2, 0, 1/2, to get, we can multiply these things out, and when we multiply them, we get a new vector. The new vectors that we get would be 1/2 x and 1/2 y, which is just the a vector and the b vector. That's what we mean by using a matrix. That's what we sort it in a matrix to actually show how you're transforming that basis. And the matrix has even more meaning. I'll show you that in 1 second. So, what am I going to talk about? Yeah, how do we know that the inverse Jacobian is an actual inverse of the Jacobian? That's the first thing we're going to talk about. Second thing we're going to talk about is vectors are represented in different systems. Actually, that can just be it for a different video. The second thing we're going to talk about is tensor transformations. Okay. So, sorry, someone just came in this room. So, how do you know the inverse Jacobian is an actual inverse of the Jacobian? How do you know going the other way will give us the inverse matrix? Well, we can actually easily prove that. So, going here, here's the equation for the Jacobian. From the Jacobian from our XY system to our AB system. It's gonna be in this format. It looks like that when we actually put in those numbers. So, to prove that it's the inverse, we have to talk about what an inverse actually is. What an inverse matrix actually is. So, for an inverse of the matrix, the inverse of a matrix, the ij component of the Jacobian multiplied by the ij component of the inverse Jacobian should give us the identity matrix of I and J. This should be A, B indices instead. Should give us the... This should just give us the Kronecker delta, pretty much. It should give us the Kronecker delta, which is just the component of the inverse, of the identity matrix, which we can just use. What should we use for this? Use JB, I think, for the component for that. Yes. Haven't done this in a long time, just saying. So, bit of review for me as well. So, multiplying these two out should give us the components of the identity matrix. So, how can we prove that? Well, we can prove that by finding... Sorry, they should be partial derivatives, not normal derivatives. They should be partial derivatives. I always make that mistake. They should be partial derivatives. So, to prove that they that it is an inverse, we can just expand partial x over partial x into the multivariable chain rule. Not just partial. That's just partial x over partial x. That plus partial y over, sorry, what would this be? Partial x over partial x times partial r over partial a, I believe, plus partial x over partial x, and this should be a b. I believe that's how you correctly expand it. And actually, wait 1 second. Okay, I believe I actually got it. It's this partial plus partial b over partial x times partial x over partial x. I believe that's how you'd expand it in terms of the a and b coordinates. I believe that's how you're going to expand it, because these have to be in the bottom. Oh, this should be over a. This should be over a. And this should be over b. Okay? So, partial x over partial x is always going to equal 1, right? So 1 should equal partial a over partial x over partial a, plus partial b over partial x over partial b. That should be 1. And remember, the Jacobian times the inverse Jacobian should give us the entries 1, 0, 0, 1. So the Jacobian times the inverse Jacobian should equal, the 1 should be partial a over partial x over partial a, plus partial b over partial x over partial b. That should be just the 1. It should give us 0, 0, and the same thing right here. Alright, actually multiply the Jacobian and the inverse Jacobian out. The inverse Jacobian would be the whole thing but flipped. When we actually multiply these things out, you would get this for the first term, and you get the same thing for, you'd actually get this. It would be y's instead for your for the bottom right term in zeros. So if you just actually multiply both matrices out, you'd get expressions that would equal 1, 1. And you can prove that by taking, I wonder, should we actually just, no, I don't have that time. So just take my word for it, or just do it yourself. If you just multiply these two matrices together, you'd get you get this expression for the first entry, and the last entry you'd get the partial y over partial y expression when you expand it out, and you get zeros for the for the 2, 1 for 2, 2 entry, for the 1, 2 entry, and then the 2, 1 entry. So yeah. And the second thing, we're gonna talk about tensor transformations. I haven't gone over any tensors yet besides vectors? Vectors are contravariant. We know that already. But the basis vectors, by definition, are covariant. That's how we define covariance. Vectors, the components, are contravariant. What does that mean? Well, it means to get a vector represented in an old and a new basis, you have to multiply that vector by the inverse Jacobian of the old vector. That makes no sense. Okay, I'm gonna go over it real quick. Covariance just means it transforms with the Jacobian. Contravariant means it transforms against the Jacobian, which is the inverse Jacobian. So to get, if I have a vector in the new basis, so let's call it V new, a vector component. Vectors are invariant. They don't change, but their components do change. The component for a vector represented with the new component would just be the inverse Jacobian times the vector in the old times the vector component in the old basis. If I have a random, I could have a random tensor that transforms with a Jacobian and an inverse Jacobian. So it would be covariant, and one's covariant and one's contravariant. That may not make any sense right now, so in the next video, I'm probably going to talk about, well, I'll just talk about how vectors transform in different bases, and after that, I'm going to talk about how vector components transform in different bases. So the roadmap for the next videos, the next direct videos, are going to be vector transformations. So now we know what transformations are. It's going to be vector transformations. Second, we're going to talk about vector component transformations, and then we will finally get to linear maps. So yeah, that's the roadmap. See you guys later.